Okay, can we start now?
Yes.
Please? Okay, so we're going to do chapter 8 today. We're going to do chapter 9 on Thursday, and then the rest of the explanation will be you guys for every single one of the cycles that we have. Got it? Step number 1, you guys will be talking about the diesel cycle. So I'll do auto today, and then you guys can take over and talk about the diesel. So today we're going to do chapter 8. Chapter 8 talks about heat to power cycle. What that means is any cycle any device that uses the transfer of heat and converts it to useful work is called a heat engine. Engineers call the useful work mechanical work, right? Because to them, all useful work is mechanical. At the most fundamental level, a heat engine is just a simple piston and cylinder contraption filled with a working fluid. And a working fluid could be gas or a gas vapor mixture. Okay. Engineers also call this piston and cylinder contraption a reciprocating engine. Just introducing you to these terminologies so it's not like it's new. So the criteria for these engines. So for a heat engine to do useful work, we need it to operate in a cycle, which means it must start at point A, go to B, go to C, go to D, and then has to come back to A, and must return to its initial state. And for most of the devices, they go through 4 steps that are standard. What are the 4 steps? What could be the 4 steps? The ones we talked about? Isobaric, isochoric, isothermal, and adiabatic. What is isobaric? Delta P 0? What is isochoric? What is isothermal? And adiabatic? Good. What do they actually look like? So an isobaric graph, so if I was to draw, oh, can I draw them all on one? Okay, so imagine I can draw all of these on a PV diagram. PV. What will the isobaric curve look like? Constant pressure. What will isochoric look like? What will isothermal look like? Very slow going down. And what will adiabatic look like? Quick.
Steeper?
Yeah, it's the slope is very big because it happens quickly. So remember the difference between adiabatic and isothermal? Isothermal processes happen over a long duration, whereas adiabatic happens quickly. Okay, now most cycles that exist are difficult to analyze. And why are they difficult to analyze? Because there is no such thing as ideal. We cannot get rid of drag. We cannot get rid of friction. So any cycle that you see will look like this. So the ideal cycle is given in black. The real cycle is given in blue. In a real cycle, do you observe? So let's start with the ideal cycle. Let's go to the ideal cycle first. If this is my point 1, this is 2, this is 3, this is 4. Yeah, tell me on a real cycle where these points are. Who knows? Is it actually at this point, or is it this point that's 1? Is this point 2, or is this point 2? Right? So our choices in thermodynamics are take an ideal cycle, do all your calculations, and then figure out how wrong you were. Make sense? And that's an engineer's job. Our job is to deal with ideal cycles. Their job is to figure out how wrong the ideal cycle was to the real one, and how to get your real cycles as close to ideal as possible. Make sense? Okay. So we will deal with ideal cycles and ignore all friction and irreversibilities that are inherently present in real cycles. Okay, what else do we know about a real cycle? We want work out. That's our useful work. And we defined it in previous chapters as QH minus QC. Do you remember doing that? And what do we need out of all our cycles? Eta. Eta is the excellent, how efficient your cycle is, which is output divided by input or cost, which means it is W out divided by QH, or QH minus QC divided by QH, or 1 minus QC divided by QH. And we talked about this. For an ideal case, this will be TC minus TH. So these are the different formulas for efficiency that you may need.
Realistically, are there only three options though? I know you've done 4 here, but there are really only 3 options.
What 3 options?
The first, work out over QH.
So they're all the same. They're literally all the same.
It all depends on what information. Yeah, I understand that. What
Yeah.
information you give you, but
Yeah.
realistically, that second option, 1 minus QC over QH, they gives you the same, requires the same amount of information as you have in the
Right, they all
so
are
I guess.
literally the same thing. It depends on what the question has given you. But in reality, yes, it will be if you were looking at a power station, you will only look at TC and TH. It is very hard to figure out QC and QH. Right? Yeah, exactly. So such as like the only thing you'll know is TC and TH. And also, even in that case, the TC may change depending on atmospheric conditions. Right? Between the winter and the summer. If your power plant is dumping the heat into the river, your TC is going to change. Because it's the river water that's going to define what your TC is. Right? So yes, in reality,